Welcome back to our course on using information theory to analyze complex systems. In this session, we're going to look more deeply at the JIDT toolkit, in particular in terms of estimating information theoretic quantities for continuous valued data. From this session, there are a number of outcomes I'd like you to take away. Firstly, to understand the different estimator types that we have for continuous data and their relative pros and cons. In particular, which of these are implemented in JIDT. I want you to be able to use JIDT via the AutoAnalyzer GUI demo to make simple calculations on continuous value data and to be able to extend the code templates that are generated for you to create more complex analyses. The primary references for this session are the JIDT paper itself, as well as the Bossemeyer and Company book on transfer entropy, section 3.4, where we go through some of these estimators. In this first short video, I'm going to talk about the nature of estimation for information theoretic measures, as well as what it means to estimate the information theoretic measures on continuous value data. So first of all, think about the nature of estimation. I want you to bear in mind that when we compute these information theoretic measures from empirical data, we're always computing an estimate. We need to recognize that our result is an estimate and not the real true underlying value. And fundamentally, this is because we need to estimate the required probability distribution functions, or for continuous data, probability density functions, from a finite amount of data. So our estimated value in the end, our estimated value is h hat compared to a true value h. Our estimator can have a bias, an expected difference between our estimated value and the true underlying value, and can also have variance, a range of estimates provided. This is when we measure these estimates across a population of realizations of the data, a population of finite realizations of the data. Both of these properties, the bias and variance, are typically more pronounced when the estimate is made from more limited data. So the more limited amount of data we have, the larger our bias and our variance can be. In particular, our estimated entropies tend to be underestimated, and our estimated mutual information terms tend to be overestimated. Okay, this is quite important, especially for mutual information. Even if we have a true zero relationship between our variables, we can get a non-zero data simply due to the bias of our estimator. So we've been looking at discrete data only so far, and the estimators that we've worked with are what are known as plug-in estimators, or a maximum likelihood estimator. I'm not sure I've used that term, but that's what people refer to that kind of estimator is, because what we're doing is we're computing a probability as effectively from a count. We count the number of times we see each symbol out of our n samples and compute that as the probability, and we plug those into the relevant equations for entropy or mutual information, etc. There are known results for the bias and variance from plug-in estimators. For example, for entropy, we can see an equation here telling us what the expected bias would look like. These are not yet included to the JIDT results, although in future I'll put an option there that you can automatically remove the bias. Let's now think about continuous valued data. The easiest thing that we can do to handle continuous value data is to bin the data and turn it into discrete data and then throw it into our discrete valued estimators. So this is what I'm showing on the slide right now. We can discretize the data by throwing down some fixed valued bins and then simply computing the probabilities from counts of how many points fall into each bin and then apply the discrete estimators. Here in this particular diagram, I've shown the bins being made at equal sizes. We can do a different kind of binning as well, which we call maximum entropy binning, where we vary the size of the bins to get roughly the same number of points in each. That only makes sense if we're computing a mutual information though, not marginal entropies. However, whichever way we do this, it's sensitive to the binning that we use, and you can see how it's sensitive to exactly where this bin line falls. If it fell ever so slightly this way, we'd get a lot more points included in these bins. If it fell slightly more that way, we'd get a lot more points included in these bins. So it's very sensitive to the binning, and it can miss subtleties in the data. In any case, it's implemented for you in the Auto Analyzer GUI. You just set the calculator type to bin, and it will take care of the rest for you. That will do equal size bins. If you want to do maximum entropy binning, you can see the matrix, the Java docs for the matrix utils class. I won't show you how to do that right now, but I will quickly go to the GUI and show you. If you come along and you select the binned estimator, and we'll just run that briefly, you can see here that what's happening is we're loading in floating point or continuous value data, and what we're doing is we're discretizing that using our matrix utils class, and then applying exactly the same discrete estimators that we used before. Okay, so that's all done for you here. The base is now the number of discrete levels that we'll discretize into. So you can see that base is supplied here to the discretized call. Okay. But there are other things that we can do. If we want to naturally treat our data in the continuous space, we're going to now turn to the differential entropy, which is slightly different to the Shannon entropies that we've been using before. This equation describes the differential entropy. You'll see now that we're using an integral rather than a sum, and we're using probability density values F instead of probability distribution values P that we were talking about before. Okay, it looks almost the same. It's kind of the way you would think about changing the Shannon entropy to use the continuous space, but there are some subtleties here. The next subtlety is we're only going to sum over, take our integral in the domain where the probability density has a non-zero value, and generally, not always, but generally we're going to take our logs in the natural units rather than log 2, and that will give us units in nats, not bits. Okay, that's important. Now, the differential entropy has some very interesting properties that are not necessarily the same as the Shannon entropy, even though it almost looks like it's a natural extension of the Shannon entropy to the continuous domain. There are interesting properties here. For example, if we shift our variable, the differential entropy stays the same, and that makes sense. The uncertainty is unchanged if we do that. If we multiply our values by a scalar, though, we get a constant addition to the differential entropy. Okay, so stretching the space changes the uncertainty if we want to think about the differential entropy as uncertainty here. Importantly, this means that the differential entropy can go negative. You could always find some scalar value to turn this into a negative quantity. What does that mean? What does it mean for what we think of as uncertainty to go negative? To interpret that, we need to look more closely at the relationship between the differential entropy and the Shannon entropy. In this last equation here, I'm using this representation, H delta, to look at what the Shannon entropy would be if we chose a discretization with bin size delta. What we see is that if we take the limit as our delta goes to 0, we get this relationship between differential entropy and the Shannon entropy, with a leftover term representing the contribution of the bin size itself. Okay, so what we're doing with the differential entropy is we're taking out the contribution of that bin size. It's also important that we think about the differential entropy as a relative measure. Okay, it's a relative measure. It's a relative measure to what the Shannon entropy would look like for a specific distribution. Okay, so here it's the distribution of the Shannon entropy, which would give, it's a distribution that would give a differential entropy of 0, and that's for a specific uniform distribution. I think from memory it's the uniform distribution on the interval 0 to 1. So when the differential entropy is negative, it simply means that it's a smaller entropy than you would have for that reference distribution. To look at a more detailed coverage of what that means, I suggest you look at Cover and Thomas chapter 8. It gives an excellent exposition of the differential entropy. So while the differential entropy itself has some odd properties, you can form all of our other measures that we've looked at as sums and differences of these differential entropy terms. For example, the mutual information as sums and differences of the marginal and joint differential entropies. Now, what's good about the mutual information in the continuous space is it's more intuitive for us than the differential entropy. It retains all of the properties, the good properties that we looked at of the discrete valued mutual information. For example, it's always non-negative. It is unchanged if we scale the variables, which is really useful. It's also exactly equal to what the Shannon entropy would look like if we discretize the data and took the limit of that discretization went to 0. These are all very useful properties that mean we can interpret the mutual information for continuous valued variables the same way as we did the mutual information for discrete valued variables. So to start estimating our information-theoretic quantities on continuous valued data, we need to understand the key here is how we're estimating the probability density functions. We're going to look in the next few short videos at the three main estimation measures implemented in JIDT, and that is using a Gaussian model, using box kernel estimation, or using nearest neighbor techniques.